So energy can change form from one type to another, but the total amount of energy never changes. This is a fundamental law in science. It's something that has been shown to be true over and over again. Now, keep in mind that we are going to be using this idea of conservation of energy. And it, again, is true that energy can't be destroyed. However, it can go into a form that's hard to get back. For instance, friction and air resistance will do work on a system and it'll turn energy into thermal energy, which again, it can be tracked, but it can't be brought back again. So in our situations to start with, we will make the assumption that friction and air resistance are negligible, meaning that there's not enough of an effect to really change the overall way the system is working. Let's take a look at a situation that involves the mechanical energy that we've been talking about. Here we have a skier who is starting from rest. We know his mass and his height above the ground, so we would be able to determine that the gravitational potential energy is 10,000 joules using the formulas that we've been learning about. I'm going to use a pi, a little circle here representing a pi, to represent the types of energy that we see here. So at the top, because the skier's at rest, all of the energy is in the form of gravitational potential. But as the skier goes down the hill and he's at a lower point, his gravitational potential energy is going to decrease. You can see that in the pi, how the blue section is a little bit smaller than the whole. And now there's this little green kinetic energy portion. But the pi itself is remaining the same size. The total amount of energy is remaining consistent. It's just changing form. And if we knew that there were 8,000 joules of potential energy by taking 16 meters times the mass times little g, we would know then also that there was 2,000 joules of kinetic energy. The total amount, 10,000 joules, would have to stay the same. And this is how we're eventually going to work in some calculations. We would be able to predict how fast the skier was going. When he gets all the way at the bottom, there is no potential energy. It's at its lowest possible point. So all of the energy is kinetic energy, represented by this pi now being all green. We could then say that the kinetic energy at that moment is 10,000 joules. And again, we could determine from that how fast the skier is going. So this idea of conservation of energy by looking at the total amount of energy at any particular position, we are going to be able to predict certain things like how fast something is going. Here's another example. There's this girl on a swing. She's at her highest point. So at this point, she would have all potential energy. And you might think, oh, it depends on this height above the ground level. But because her lowest point is actually going to be where this dotted line is, we are going to think of her potential energy as being measured reference to that point instead. Her path is going to sweep down along this curve. And so the lowest point is where this black dotted line is. And we could now choose that as our reference point. So as you're thinking about the conservation of energy, what's going to be important is not necessarily, reference to the ground, how high something is, but maybe just reference to the very lowest point. When she's at this point, if we take this perspective relative to that lowest point, now she has just kinetic energy at the bottom. And this is going to be a nice way to think about it because it's all potential turning into all kinetic. Now, if she's somewhere in between, then there's going to be a little bit of both. But the total amount, again, is going to remain the same at each of these points. That is what the law of conservation of energy is all about. Let's see what this looks like as a formula so that when we get to some calculations later, it'll be familiar to us. We're going to say that energy is conserved as long as there's nothing external happening to the system, meaning that we don't have things like friction or air resistance stealing energy away by doing work on our objects. And in this case, we could set up an equation where the total initial energy, whatever types of energy we have at the beginning, is going to equal the total final energy. And when we say initial and final, we really just mean any 2 points within the object's motion. We'll use a sigma symbol to represent the total, like we've done before in our class. We want to be able to build equations that relate the initial energy to the final energy. This is going to be the goal as we move through this section of our class. That means that we are going to think about all the different types of energy that an object might have at different locations, at different moments of its motion. And so we'll have to consider, does it have an initial kinetic energy, an initial gravitational energy, an initial elastic potential energy? And then at a later time, we'll have to consider those same 3 things. So we're going to have a sense of, how do we decide whether something has these different types of energy? At each location, you're going to want to ask yourself, is the object moving? If the object is at rest, then it has no kinetic energy. But if it has motion, if the problem talks about it having a speed and so forth, then we're going to consider it to have some kinetic energy, 1/2 mv squared. And then in terms of its vertical position, if it's elevated above its lowest point, then we want to consider it to have gravitational potential energy. And we can make the choice of calling the lowest point the 0 point if we choose to, and then have everything else measured from that point. We'll see that when we get to the calculations. And then the last question we want to ask is there some sort of elastic material, like a spring or a rubber band, that's being stretched or compressed? And if it is being stretched or compressed at that moment, if it's not relaxed, then it will have there will be elastic potential energy. So let's look at an example here. This is a wind-up toy. Maybe you've seen one of these things before. So you have a little key that you wind up, and what's actually happening is there's a spring inside that is being stretched or compressed. It's being adjusted so that there's energy stored in it. And so at this moment, we could ask, is the object moving? Well, nope, it says it's at rest. Is it elevated above its lowest point? Well, this little rabbit toy stays at the same level all the time. So I don't really have to think about gravitational potential energy. But is there something stretched or compressed? Is there energy stored in something elastic? Yes. Okay, so at this point, at point A, there would be elastic potential energy. Now, after it's released, the toy starts to move. Aha! If it's moving, it has kinetic energy. And at point B, it's not quite all released yet. And so there would be some elastic potential still, but it's going away. Okay, it's being transformed into kinetic energy, energy of motion. But again, the pie is the same size. The total energy is remaining the same. But at point C, the problem says that the spring is completely unwound. And so that means there's no energy stored anymore in that elastic material. All the energy has to be in the form of kinetic energy. It's all due to the object's motion. And so if we were going to do a problem, we would be comparing either position A to B or B to C or A to C. And that's how we're going to be building equations to predict what's happening in certain situations. Let's look at one more example. So here we have a skateboarder at position A pushing off with a small starting speed right at the top of a ramp. All right, so is the object moving? Yes, because the problem says there's a small starting speed. It gives us that information. So there's going to be some kinetic. Is the skater above the lowest point? Absolutely. Okay, the lowest point is seen here in figure C. So it's above that point, so there's going to be gravitational potential energy. Is there some sort of elastic material that's being stretched? Nope, that's not mentioned at all in the problem. So this question is only going to deal with kinetic and gravitational potential energy. And as the skater goes down, the potential energy is decreasing because the height above the ground is decreasing. And that means the kinetic must therefore increase. The total pie has to stay the same size. And so the total energy is staying the same amount. That's what we mean by energy being conserved. And then when we get to the last point, the skater is at the very lowest point. So he's no longer elevated above the lowest point. There would be zero gravitational potential energy. All of the energy would now be in the form of kinetic. So again, these are some visuals to help us understand the law of conservation of energy. And then in the next video, we'll talk more about calculations and using these ideas to predict what happens for a certain object's motion.